You could take GRN for one trade car and then sell this thing. Where's Mike?
Okay, let's get started. So I want to do a couple from today's homework. So here's one that caused more difficulty than the others. It didn't cause a lot of difficulty. So before we just start moving symbols and trying to get an answer, let's break this down. So I'm looking at this right here in parentheses, cosine x minus 3. So let's see here. Connor, do you have a question?
I was just going to note that, like, some people may have screwed up because I thought it was cosine of x minus 3.
Okay, so again, I want to talk about meanings. I want to talk about meanings, not getting the answer. Okay? So let's look at the cosine x minus 3. Let's see here. Christina, so in this expression, cosine x minus 3, what would that be? What would that mean? Cosine x minus 3 is the antiderivative. Talia, do you agree with that? Okay, so we got it's an antiderivative and we got it's a derivative. Let's see. Jacob. Okay, but what does it mean? So when we look at that and you see this. Say it again. So you're saying this is a rate of change function. Is that what you're saying? Yeah. He's saying this is a rate of change function. Yeah, so yeah, we've been talking about that all semester. Yeah, this is the rate. So this is a rate of change function. Maybe, all right, let's call it that. Okay, so then what would cosine x minus 3 times dx mean? So all of this. Cosine x minus 3 times dx. Zoo. All of that. He said the accumulation for a very small x interval. What were you going to say, Marcus?
I want to say the rate of change will just change for small bits of x.
So it's still a rate of change. When we multiply by dx, it's still a rate of change. So you agree with him? So he's the accumulation for a very small x interval. Yeah, good, right? So this is our little bit of accumulation, very small bit of accumulation. Okay, so now let's do the whole thing. What does the whole expression mean? Judith.
It's the accumulation from negative 9 pi over 2 to 9 pi over 2.
Okay, of what?
What do you mean?
So it's you're saying it's accumulation, but what is accumulating?
I mean, it doesn't have units, so I don't know.
Okay. Is there a way we can express what's accumulating? Sharon.
The accumulation from the lower bound of the accumulation function, the weight function is
Okay. So she said what's accumulating is some function whose rate is cosine x minus 3. Would you agree with that? Yeah, so this implies that there's some function, accumulating function. And we know its rate. And this is going to calculate the accumulation from negative 9 pi over 2 to 9 pi over 2. Okay? So, well done. Okay, good. So now, how do we get that? So how can we get that amount of accumulation? Okay, antiderivative. Okay, so this is really expressing the accumulation as bit by bit, right? Bit, 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 bit. But we have now, we know a way to actually calculate that without adding up a million zillion bits. Lauren, how are we going to do that? Okay. So there's some function, and you're going to take it of the higher bound minus the lower bound. What function is that, Lauren?
It's the antiderivative of the rate.
Okay. And what does it mean?
It's the accumulation.
Right. Oh, so it's just, yeah, it's the accumulation function that has this rate, and you said it's the antiderivative. So take over from here. Let's see, Beth. So, what should we do to check? Take the derivative. Do it. So we're taking the derivative of sine. Don't make a change before you haven't, like actually take the derivative.
Because n is minus 0 raised by
Okay, so Beth, what's the derivative of this? No, the derivative of sine is what? Just cosine, okay? What's the derivative of this? So, did we get it? What do you need? That's 3x. Okay, and we're going to take that from? Okay, so Connor, this might be the time to chime in. So now we're getting to the solving part. So what were you saying?
Oh, no, I was just pointing out that people got it wrong. Might have been because people thought it was the cosine of x minus 3. And that's,
Oh,
I tried to
the
answer it
expression.
like that. Yeah, and then like confused me. So I was just pointing out that maybe people might have done that. I don't know that I did that, so.
Yeah, you would have to, there would have to be parentheses around the x minus 3.
Okay.
You would, yeah. This is showing,
It's just like,
okay, gotcha.
you want me to answer?
Sure, you can keep going if you want.
Alright, well, just, you can just do addition of functions. And, it's one function being cosine x, the other one being negative 3. And you just apply that, find the antiderivatives of cos x and negative 3, which is sine x and negative 3x.
Okay.
And then, well, you do big F of, what is that? Is that 9 pi over 2?
Uh-huh.
And then minus big F of, negative 9 pi over 2, which is big F, what I just described.
So here's the thing that is an easy mistake to make. When you subtract the function, the accumulation function with that plugged in, you got to subtract the whole function. So use brackets, because a common mistake would be here to subtract sine and then subtract this 3x, when really in the end we're going to do what? We're going to add that, right? So subtract the whole function with the lower bound plugged in, meaning you're subtracting this whole thing. Where is 9 pi over 2? 8 pi over 2 is, that's 3 o'clock, so we're going to go to the pi over 2. So that's the top of the circle. And negative 9 pi over 2 would be the bottom of the circle. Is that right? So this is 1. And it looks like we got minus 3 and then minus, minus, minus. So we're going to have 2 of these. We're going to minus 3 times 9 pi over 2, and then minus 3 minuses make 2 of these, so it's really going to be minus 3 times 9 pi. Run out of space here. So it's going to be 1 minus 3 times 9 pi. And then this is going to be negative 1, so plus another 1. So I'm seeing 2 minus 27 pi. Questions on this example?
Okay, so right there at the very end, you lost me, where you went
It-
from
So I don't,
expression to
you can do it. Just go slower. It's just arithmetic. So stick with the you know, you can do the arithmetic if you just go a little slower. I just went fast. Just the key is when you do this, when you plug the negative 9 pi over 2 in, just make sure that you subtract the whole thing. A common mistake would be to go minus sine of this minus 3 times that, when really you're subtracting the whole thing, so you have a minus and a minus there. See that?
so you have plus 3 times.
Well, no, but then this is also negative, so then it's 3 negatives. Makes a negative. Okay, now the one I want to talk about, this is an important question here. Let's talk about this one. Okay, so what's dp over p squared? David, what does that mean, dp over p squared? Okay, we can rewrite it. And then what does that mean then? What does that expression mean? 1 over p squared times dp. So it's the rate of change. Daniel S., what do you think? Is it the rate of change?
That's the rate of change function.
1 over p squared times dp is the rate of change function.
It's the accumulation over. Well, it's the rate of change times tiny bits of accumulation.
So this is the rate of change, and this is a tiny bit of accumulation. Agree with that? DJ?
Well,
No. So what? Yes. Adelaide?
Yeah,
Rate of change. What's that? Okay, I'm not sure what you're referring to. So what does the whole thing mean? Or your choice. Either tell me what the whole thing means or tell me what they mean individually.
Well, 1 over p squared is rate of change. And then dp is small changes in p.
Small changes in p, okay. And so what is it together? Lauren?
Accumulation.
What's that?
Accumulation.
Accumulation.
Yeah, accumulation from. Are you talking about the entire thing?
No, well, I just put this, what I'm putting a bracket around, this expression right here, which is dp over p squared.
Yeah, it's rate times like delta x.
Okay.
Yeah, so little bits of change.
A little bit of accumulation. Tiny bit of accumulation. Okay, so, and we're going to accumulate here from Tyler.
And accumulate from 4 until x cubed.
Okay. So then that's going to be, will that be an amount of accumulation or will that be an accumulation function? Andrew, Laux. Okay. So we'll get some accumulation function. And then, what will the whole thing mean? Stanley?
The entire thing is the derivative of some accumulation function, which we already know the rate of.
Okay. What's the derivative? So
It would be 1 over p squared.
I don't know, not what is it, but what does it mean? So,
So the rate of change of that accumulation function.
so the rate of change of this accumulation function, for which
1 over p squared is the rate.
1 over p squared is the rate. So it's the rate of change of an accumulation function for which 1 over p squared is the rate. So, is it 1 over p squared? If it's the rate of change of an accumulation function whose rate is 1 over p squared. Is it 1 over p squared? No. Is it 1 over x cubed squared? Sorry, I should have said 1 over x squared here. So it's not 1 over x squared. Is it? So maybe it's 1 over x cubed squared. Talia says no. She's right. It's not. Okay, so if you try to fast track it on a problem like this is on the final, by the way. Okay? Very few people got it right last semester. Okay, so this is important because it incorporates so many things and so many meanings that it's a great question to see if you understand what's going on. So if you try to fast track this and say it's 1 over x squared or 1 over x cubed squared, it's not right. So we've got to take the long route and just work this out step by step. Okay? So let's do that. So what can we do first? Who said that? Adelaide, what do you want to do first?
Take the antiderivative of 1.
Perfect. What's that? Right, negative p to the negative 1. I'm going to write that as negative 1 over p. Is that okay? And then we're going to evaluate that from 4 to x cubed. And then when we're done doing that, we're going to? Yep, that's what it says. Okay, so let's do that inside part first. We're going to have negative 1 over x cubed plus 1/4. Check my work. Is it okay? Okay, so derivative of negative 1 over x cubed. Corey. So change it to this first. 3x to the negative 4th. And then derivative of 1/4. 0. So notice we got 3 over x to the 4th, which is neither 1 over x squared, nor is it 1 over x cubed squared. So what's going on here? What happened? Anybody? Want to offer up? Why isn't it just, if it's the rate of an accumulation function that has this rate, why isn't it that? Or why isn't it just plug x cubed into that, 1 over x cubed squared? Any ideas? Yeah, Tyler.
Because normally when we do that, we have it from a certain point to another point, some constant value, like 1/2 or whatever. Because once you put an x cube up there, it's some function. So you have to take the derivative of the f of x cubed minus the f of a.
Okay. All right. So let's do it a second time, and we'll see what comes out here. So instead of actually finding this antiderivative, since we're going to take the derivative of it again, let's just call it capital F of p. Can we do that? So instead of actually finding that antiderivative, we know we're going to eventually take the derivative of it again. Let's just call that antiderivative capital F of p. Is it fair? So tell me what that thing in parentheses is. Dan.
Capital F of 4 minus capital F of x cubed.
Capital F of 4 minus capital F of x cubed. Do the final minus initial, right? Okay? And so now we're going to do it's just the sum rule. Okay, so what's the rate of change of capital F of x cubed?
Let's see.
What was capital F again? What kind of function was capital F? What is capital F? Rate of change function. Is that right? Adonijah, what kind of function is capital F?
It's the accumulation function.
Okay.
First integral.
And what do we know about that accumulation function? Capital F. Do we know anything about that accumulation function in order so that we can take the derivative? Yeah.
Oh.
It has a rate of 1 over p squared. Is that what it is? Yeah, this is the accumulation function whose rate is 1 over p squared. Okay, so what's the derivative of it? So 1 over, but we don't have p now, we have q, so 1 over x cubed squared. Is that the derivative? Why not? Taking the derivative of capital F of x cubed. What's going on there? Any ideas? Speak up if you're thinking of something. Taking the derivative of capital F, some capital F function with x cubed plugged into it. Marcus? Chain rule, yeah. It's chain rule, right? So are we done here with this derivative? No, so we do the derivative in the overall structure, which is our 1 over p squared or 1 over x cubed squared, and then what else? Times 3x squared. Derivative of the accumulation at 4. 0. So what do we get? We got 3x squared over x to the 6th equals, what happened? See? So why isn't it 1 over x squared and why isn't it, or 1 over x cubed squared? This is actually closer. This is a little better than this. Still not right. Why not? Right, because so when we get this accumulation function, we plug x cubed into it. So now when we take the rate of that, that's going to require the chain rule. So this accumulation function really doesn't have this rate anymore when we plug some other function into it. When we plug another function into it now, it's a different accumulation function than the one that has this rate. The new accumulation function, when x cubed is plugged in, has this rate. Talia?
You lost me at the d over dx times of capital F x cubed minus capital F.
Okay, so tell me what this means. What does that mean?
Taking the derivative
Uh-huh.
of the function at
Capital F.
x cubed.
So we're taking the derivative of this function, which is capital F, with x cubed plugged into it. So how do we do that? How do we take the derivative of that? So we need to know the rate of change of capital F, right? What's the rate of change of capital F? Isn't it 1 over p squared? Because that's what we said capital F was in the first place. It was the accumulation whose rate was 1 over p squared. So now if we're going to take the rate of that, it's just going to be 1 over p squared. But x cubed is plugged into it, so it'll be 1 over x cubed squared. And then because the x cubed is plugged in, it's also by the chain rule we need the 3x squared. Is it better?
Yeah.
Okay, really important problem. So make sure you understand all the... So notice how we kept talking about meanings of everything as we went through it. That's what allows you to solve it instead of just kind of memorizing how to push the symbols, right? The meanings drive how you understand it and your ability to work it. Okay? Any questions? Okay, yeah. Oh.
Why is it squared at the bottom when you take a capital F of x cubed?
Okay, so tell me what capital F of x cubed is. What is that?
That's the accumulation of x cubed.
It's not the accumulation of x cubed. It's an accumulation function. Yeah, with x cubed as its input. So we need, in order to take the derivative of that, we need to know more about that accumulation function. What else do we know about that accumulation function? Capital F. How did we define it? We made it up, right? We said capital F of P was an accumulation function with what? That has this rate. Yes, this accumulation function that has this rate. So now what are we doing? We're taking the derivative of it.
But I don't get how it's cubed. Like I see how you got 1 over x. I don't get why it's squared.
What is the rate function for capital F? What is the rate function?
Yeah, I got it.
See it? Yeah, it's 1 over p squared. See?
Yeah.
You see? Okay, good. Glad you asked. Other questions? Okay, so let's, in terms of these are the antiderivatives getting better? Like, do you feel like you're thinking backwards? It's kind of like like one step more difficult. So because all the derivatives are basically just learning the rules and practicing, but then going backwards is kind of like one step more difficult. So let's talk about some harder versions of those. Need to go to a different course for that. Okay, so I got all the blank versions of the quizzes and all the solutions up for the quizzes. And you got the review outline. Your exam is tomorrow. So, time to hit the books. Okay, this is an important exam. Please, in the middle and toward the end of your studying, please come in and see Owen, see myself. It's these conversations that are going to boost your understanding of it when you bring your questions, things you don't understand. And we sit and we talk about problems and concepts and ideas that's where you fill in the gaps, you start making connections, things really start to gel and make sense so that you can succeed on the test. So I'm actually available today at 2:45 in my office. Okay, so if you want to come by today, and if you're going to come much later than that, shoot me an email to make sure that I'm still there, but I'll be around at 2:45. And then I can possibly, my normal office hours tomorrow are at 2:30 to 3:30, but I have availability earlier in the day. So if you want to send me an email, make an appointment, I'm happy to do that. Okay? So come in groups and we can just have a study session. Okay? And then yes, my thank you. My hour in the testing center is from 1 to 2. Yep. And so if that's the only time you can come, I can slip out of there and you can ask me a question in the hallway even. All right? Or we can sit down for 5 minutes and talk. All right. So where is this one? Wrong one. Here it is. So the harder antiderivatives would be the ones that are a result of more complicated derivatives. For instance, the chain rule. So the chain rule is it's a more complicated process. So undoing the chain rule will take a little more. It'll be a little more difficult. Take a little more practice. Let me find a good one here. There we go. There's a good one. Okay. So what is the chain rule? So when do we use the chain rule on what kind of function? So what kind of function would we have that we would use the chain rule? Yeah. Do the set of function inside a function. So one that looks like that. That's what we call a composite function. Okay? Composite function. And so when we take the rate of change, how do we take the rate of change of a composite function? Or what is the chain rule? So we look at the overall structure, which is it F or G, the overall structure? F. So we're going to take the derivative. And then are we going to also take the derivative of G? Not yet, right? And then? So in general, when you have a chain rule derivative, how many factors does it have in general? What's that? Yeah, you got this part, right? And you got this part. So when we're going to try to undo the chain rule, this is what we're looking for. We're looking for two things multiply. Okay? And so then which one of these two, so then taking the antiderivative means kind of collapsing these two pieces back together into one piece. Do you see that? So which of the two pieces, the first or the second, would we want to focus on in order to recover the original function? Would we focus on part number 1, or would we focus on part number 2 to recover the original function?
Part 2.
So we've got f prime g times g prime. We're trying to recover f of g. So which one of these two is going to be most helpful? Yeah.
I would say part 1, because once you figure out what f is, it already gives you g. You
Right.
don't have to do anything.
Exactly. So really, all we have to do is look at the overall structure, which is the exterior function, and do what? Take the antiderivative, g, and leave that g thing as it is. You see? So once we recognize that we're undoing the chain rule, we just need to figure out which part is this part. And then we just do the antiderivative of f. And then there's a little mess to clean up. But that's the basic idea of it. Do you see? Okay, so step 1 is to identify f prime g. And then we could do a little check. Before we start actually doing the antiderivative, we could check what?
If that g that you found, it's prime, like its derivative is somewhere in your original.
Right. So we could take the derivative of this interior, and that should be present also. That should be the other piece, you see? Check g prime. Check to see that that's the other piece that we have. And then now we're ready to start. We can do our first, what we'll call our first attempt. And the first attempt will consist of, just in general, basically what, Sharon?
Like in general? Or
Yeah, we're going to take our first attempt at taking this and finding its antiderivative. So what will that look like? What will we do?
take the antiderivative of this.
What's that?
Take the antiderivative of the first part.
Yeah, so we're going to take the first attempt will just simply be taking the antiderivative of the exterior function. So it's first attempt is the antiderivative of f prime. Leave g plugged in. Okay? Then what are we going to do? So with all these, what do? We've got our first attempt at the antiderivative. Take the derivative. And compare our derivative with what we were given in the first place. If they match, then what? We're done. We got it. If they don't match, adjust. Second attempt. If needed. So the whole thing here is about thinking about the chain rule, right? And we're going backwards on the chain rule. So really understanding the chain rule is going to help. So here we go. I've got this one. Let's give it a shot here. X cubed plus 3x times x to the 4th plus 6x squared plus 2 to the 6th dx. Does it look like it could be the result of a chain rule? Yeah, because there's two pieces here. Okay, so we want to see that as f prime of g times g prime, if it is indeed the result of a chain rule. And we want to focus on, we want to find which one looks like f prime of g. So the first or the second, f prime g. The first one or the second one? People are saying the second. How come? It's raised to the 6th power, and then how can we check? How can we do a check here? Take the derivative of the inside, and what do we get? 4x cubed plus 12x. So 4x cubed plus 12x, is that basically the same as that? Yeah, it's just basically by a factor of 4, right? Or 1/4. So yeah, so it matches. 4x cubed plus 12x is basically, we know that we can multiply factors all day long as we go derivatives and antiderivatives, right? And they just stay around. So 4x cubed plus 12x is basically 4 times that. So we got it. So first attempt, what will it be? Who wants to do the first attempt? If this is our, so what we said is, this is our f prime g. And so our first attempt will look like what? So using these symbols f prime g, what will the first attempt look like? Using these symbols f and g and prime and all that, what will the first attempt be like? What's that? F of g. Just like we said, we're going to focus on this part, and we're going to look at the overall structure, antiderivative. It's the same thing. It's shorthand. Yeah, shorthand. I'm not using the. I'm not putting the x's in. But yeah, same thing. Okay, so let's do it. Who can tell me what the first attempt at this antiderivative will be? So we're right over here. First attempt.
1.
I saw Lauren. She beat you by a hair. Go.
Is it like 1/7?
1/7.
Times the in parentheses,
Okay.
raised to the 7th?
Raised to the 7th. What do we think? Did she do the antiderivative of the outside structure? Yep.
Derivative of g is going to be 4x cubed, though. You still have to deal with that.
Okay, so what do we so? Are we done?
No, we still have to get G prime.
Also, is this improper or proper? Improper, so we need?
C.
Yeah, because we want all, basically this represents all antiderivatives or all accumulation functions that have that rate. Okay, and we know that there's that possible constant. Okay, so that's our first attempt. So then what are we going to do? Take the derivative. What will it be? What's the derivative? Okay, so what we got here is something to the sixth. We have something to the sixth, right? And we're doing the antiderivative. What's the antiderivative of something to the sixth? No, that's the derivative. Antiderivative. Antiderivative. 1/7 x to the 7th, right? Okay, so who wants to take it here? Andrew.
So that's 1 times that quantity is 6.
Okay. Done? That's the derivative? Times?
Times the derivative of that.
Tell me.
4x cubed plus 12x.
So now what do? We compare this to what we had to start. Are they the same? If they're not the same, how do you want to adjust this first attempt so that if we took the derivative of it, we'd have exactly that? Talia, how would we adjust it? So second attempt.
So I would do 1/7 times 1/4.
1/4?
No, like in parentheses 1/4 x to the 4.
We can't put anything inside the parentheses. We're not allowed to because it's to the 7th.
Like on the outside of the one side.
Okay, so what is this the same as? This is just the same as x cubed plus 3x times what? Times 4. So it's not there's nothing inside the parentheses that we need to do. Our derivative is 4 times the original rate function. So we just need 1/4. And now when we take the derivative, we're going to have the same thing here, plus, and with also multiplied by 1/4. Okay, did I lose you? Does that make sense, Talia?
Yeah.
Really?
Yeah.
Okay, did I lose you? Does that make sense? Yeah.
I have a question.
Sure.
On proper integral, so say we have bounds, do you stick with the plus c? Because you said with improper you put the plus c and then.
Yeah, so it can represent. So with a proper integral, you can choose any antiderivative that you want. All right. So you can add anything that you want. You can take any. So the fundamental theorem from A to B says that it equals f of b minus f of a, where capital F is any antiderivative. So meaning when you have the bounds, you can put plus c there, you can put plus 1, you could put minus 100, you could put plus 0.
As long as it's not a variable. Like not like x.
It's a constant, right? It's like, yeah, because it has to. It's any antiderivative of this. So you can choose any one that you want, and so the easiest one to choose is the one that's plus 0. Does that make sense? But with an improper integral, you have to show that it's all of them by saying plus 0. Okay, did I lose anyone in this process of finding this antiderivative? Okay, so I'm going to give you a practice problem, and you guys can work on it. See how we do. I'll write it bigger. we go. Okay, find the antiderivative. That's not the fifth root. That's to the fifth times the square root. And this is 3/2.
No, fractional. Bring that power down, that's 1/2. Are you asking what fraction? No, you need 2 of it. Because that's gonna bring down, it's gonna bring down. That's what we need to cancel out. So 2 for 1.
I'm just gonna leave it like that. Just leave it here.
Yeah, just because of what's going on. Plus
Okay, Megan, did you get a first attempt at this one? Tell me. Oh, you just went for the whole jugular.
well, I mean, if that was her first attempt.
Yeah, that's a good first attempt, right? Yeah, so if you can see it, if you can see all the factors that you need to do, that's great. But if you can't, so how would we, first of all, which is f prime g, this one or this one? This is our f prime g. And so in general, what are we going to do? Marcus, do you want to try?
Also from the x to the rest of the fish, I'll put it at 1 over 6 at the time of the inside plus 3 raised to the 6 and then
Plus,
so it's 2/3 1
no.
c.
Plus c. Okay. All right. So then, what do we do? Take the derivative. We're going to get
X 3/2 plus 3
to the fifth.
times 3/2 x to the 1/2.
Is it exactly the same as our rate function?
Almost.
What do we need? How do we need to adjust our first attempt so that when we take the derivative of it, we'll have exactly that and not that?
Cancel that.
What? So Megan, which is what? So she wants to multiply our first attempt by 2/3 so that that goes away. Is that right? So our second attempt then, 1/6 times 2/3 times. And we could simplify this to 1/9. Is that right? That's just the same as 1/9.
Your second attempt needs to be to the 6
Is that right?
We did a 6.
Oh, this is a 6 here. That's something I knew something was wrong.
Close enough.
Not for calculus. All right. So what I'm going to do is I'm going to post this My Math Lab homework practicing this undoing the chain rule, but we'll make it due Monday along with Friday's homework, so that you're not attending homework the day after your exam. So I want you to focus on the exam. If you want to get started on this in the meantime, you're welcome to, but it won't be due until Monday. So focus on your exam. Focus on your exam. I'll be in my office today, 2:45, and then tomorrow I can be around if you need me. When do you want to come? Yeah. An hour, at least? Yeah.
You walk away from me now, I've never seen you like you can see my little right, I'm sure that slide back to
Yes.
Is the test all multiple choice or are there free
Yeah. It's all multiple choice, but don't study any differently.
How many questions are there?
It's pretty similar to the last one. I think it's like around 30, 35, something like that. Which is,
Oh.